Sampling distribution of the mean. This section will discuss some important properties of the sampling distribution of the mean. You can think of the sampling distribution of the mean as the distribution you would get if you repeated sample n numbers from a distribution, computed the mean of the n numbers, and then plotted the result as a relative frequency distribution. One important property of many distributions is the mean. The mean of the sampling distribution of the mean is the mean of the population from which the scores were sampled. Therefore, if a population has a mean of 5, the mean of the sampling distribution of the mean is also 5. The symbol mu sub m, or mu sub x bar, is used to refer to the mean of the sampling distribution of the mean. Therefore, the formula for the mean of the sampling distribution of the mean can be written as mu sub m equals mu. The variance of the sampling distribution of the mean is the population variance is divided by the sample size. The sample size is the number of scores used to compute the mean. The formula at the bottom is the formula for variance of the sampling distribution of the mean translated into symbols. The variance of the sampling distribution of the mean is repeated, with the symbol of sigma squared sub m. The variance of the population is represented by the symbol sigma squared, and the sample size, the number or scores used to compute a mean, is represented by the capital letter N. As you look at the formula, notice that as the sample size gets larger, the variance of the sampling distribution gets smaller. For example, if the variance of the population were 30 and the sample size were 5, then the variance of the sampling distribution of the mean would be 6. Now we see a comparison of a sample size of 5 with a sample size of 10. In both cases, the population variance is 30. For the sample size of 5, the variance of the sampling distribution of the mean is 6, whereas for n equals 10, the variance is 3. Notice that doubling the sample size cut the variance of the sampling distribution of the mean in half. The standard error of the mean is the standard deviation of the sampling distribution of the mean. Therefore, the square root of the variance of the sampling distribution of the mean can be written as shown here. The symbol of the left represents the standard error of the mean. It has a sigma because it is a standard deviation. The subscript m indicates that the standard error in question is the standard error of the mean. The numerator of the right side of the equation contains the population standard deviation. The denominator is the square root of the sample size. The central limit theorem states that, given a population with a mean mu and a variance sigma squared, the sampling distribution of the mean approaches a normal distribution with a mean of mu and a variance of sigma squared over n. As n, the sample size increases. Remember that the sample size is the number of scores that a mean is based upon. What is remarkable about this theorem is that regardless of the shape of the parent population, the sampling distribution of the mean approaches a normal distribution. Here is an example from the central limit theorem demo. You may have already seen that yourself. This figure shows the results of the situation for n equals 2 and n equals 10. The parent population was a uniform distribution. You can see that the distribution for n equals 2 is far from a normal distribution. Nonetheless, it does show that the scores are denser in the middle than it is in the tails. For n equals 10, the distribution is quite close to a normal distribution. Notice that the means of the two distributions are the same, but that the spread of the distribution for n equals 10 is smaller. This figure shows how closely the sampling distribution of the mean approximates a normal distribution even when the parent population is very non-normal. The distribution at the top is the parent distribution, and the two figures below are the estimates of the sampling distribution for n equals 5 and n equals 10. The distribution of means for n equals 5 was created by repeatedly sampling 5 scores from the top population and computing the mean for each sample of 5. The figure is a plot of these means. The distribution of means for n equals 25 was created the same way, except that the sample size was 25 instead of 5. If you look closely, you can see that the sampling distributions do have a slight positive skew. Nevertheless, the distributions are much closer to a normal distribution than is the parent population, the one at the top.